All right, looks like we're live. Hello and welcome to another Zozin session. How about that? How about that? I bet you didn't expect that shit to happen. So, let's make a little bit of an announcement as usual and post a message on our Discord server. So, red circle live on Twitch. And today we're doing functional programming. That's what we're doing today. So I need to also give the link to the Twitch channel. So it's going to be twitch.tv/Zoding. And we're going to ping everyone. Everyone is binged. Everyone is binged. So hello chat, hello Demke, hello to be Prime, hello, welcome. So what are we doing today? Today we are solving 99 OCaml problem, or 99 problems on OCaml. So basically this is a set of problems, like 99 problems, which is inspired by 99 Lisp problems, which in turn was inspired by a Prolog problem list. So essentially it's more of like a challenge, right? So if you are learning OCaml, you can basically practice your OCaml skills in the like using this set of problems. Some time ago, I think, like, I don't know, I think I was not already a student. I think I graduated from uni, but some time ago I already attempted to solve some of the problems, and I think I still have like a repo on GitHub where I try to do that. So let's actually search for OCaml in here. Yeah, 99 OCaml problems in 2013. Oh my god, I was a student. I was actually a student. I was in uni when I was trying to solve. Okay, so I managed to solve like 25 of them. So yeah, so, but that was a long time ago, like 8 years ago, and this is 8 years is the last update, right? It's a last update, and I started this entire thing. Well, I mean, yeah, I basically briefly tried to solve this entire thing, and I just like stopped. Right. So back when I was a student, I managed to solve 25 of them. So I'm not going to look into any of these solutions, and I'm going to try to attempt to solve them today with my current knowledge and see how much I degraded as a developer, right? Because I'm getting older, I'm getting dumber, I'm losing brain cells, so probably I won't be able to solve 25 of them today. So yeah, I'm gonna give the link to this repo in the chat, and for people who's watching on YouTube, I'm gonna give the link in the description. My old attempts at solving these problems, right? So, but today we're gonna actually start in a completely fresh and new repo. We're gonna start on GitLab because the buttons on GitHub are poo-poo. We already established that the buttons on GitHub are shit, and that's why we're using GitLab. Tiny CLG, thank you, CLJ, I'm sorry for my English. Thank you so much for 3 months of Twitch Prime subscription. Thank you, and welcome to Epic OCaml Club. That's right, we are OCaml developers. So, alrighty. So, and for those who doesn't know, OCaml is a functional, sort of like functional-ish programming language. It's more of a like, you know, multi-paradigm because it also has OP part that nobody uses, and also it has imperative parts, right? So essentially it has like a seamless experience between functional programming and imperative programming. It also claims to have object-oriented programming, but nobody fucking uses this piece of shit, right? So everybody who programs in OCaml, they usually use the functional aspect of OCaml and imperative aspect of OCaml, right? So object-oriented programming, I think they just added it because at the time of the OCaml development there was like a huge hype around OOP, so to market the language better they just added OOP, well, because of the time. So, and since there's already code that depends on OOP features, I presume the object-orientedness of OCaml was left as a scar on the face of the language, right? You cannot really get rid of it because there's still code that uses that, but at the same time the new code rarely uses those features, so you don't really know what to do with this shit, so it's just like there, right? So that's what usually happens with features like that. So I presume it's purely for like marketing purposes. So It's rather interesting. It's rather interesting. It feels like Haskell, but it's not lazy, right? So one of the things in a camel is that it's not lazy, but it has lazy evaluation, right? Just in case you need it, right? Hello, everyone. Hello. O_camel user says a camel is cool. Well, thank you for your unbiased opinion. Thank you so much. Yeah, I also think that a camel is cool. So, how are you guys doing? Hello, Disused, Demke, Fluffy Poga, Eddie, Poppet, Chan, Crazy Chicken, so many cool names. Hello, welcome. Cheers, by the way. Alrighty, so let's actually clone this repo and let's take a look at the problems, shall we? So this is a Zozing and I'm gonna do git clone. Do I even have a camel installed on my machine? I do. I have a camel 4.10.0 and I'm not even sure if that's the latest camel, but a camel is not Rust, you don't have to have the latest camel, right? So got him. Alright, so we have this readme and so this is like a crap that was auto-generated by GitLab. So I think I'm gonna actually remove all of that. So at least for now. So we're only gonna have this thing. And in terms of the license, I'm gonna distribute all of that under MIT license, so you can do whatever the fuck you want with it, right? Except claiming that you made this thing, right? So this is basically MIT license. Do whatever you want, except claiming that you created this thing, including selling, by the way. You can make money off of the code, just don't say that you made it, right? So this is that. So let's create a simple hello world in a camel. I wonder if I still remember how to program in this language. So while a camel from 8 years ago is probably the latest, so effectively you have the latest camel without even trying. What's funny, when I was solving this problem, I think a camel didn't even have the pipe operator, right? So, and the pipe operator essentially allows you to sort of pipe values through a sequence of functions and so on and so forth. I'm so fucking old. I remember a camel not having this operation. That's how fucking old I am. So, and I remember the times when I was ranting about a camel not having this operation, right? And how all of the other languages, or all of the other cool kids do have it, and I have to implement that operator myself. That's how fucking old I am. So, oh shit. Boomer Zozin, yeah, exactly. Boomer Zozin. Okay, so let's actually write hello world. I think you write it like this. I almost actually wrote hello world and then print end line, because I've been programming in Porth too much lately. Right, because right now I'm actively rewriting Porth in itself, and in fact, right, so I think it's already like 1,000 lines of code or something. I don't fucking remember. So let me take a look at the current state of Porth. So I'm gonna fetch the latest shite and take a look at the Porth. Porth.porth. So here's the current state of Porth. As you can see, I already added all of the intrinsics. Adding all of the intrinsics was relatively simple because we already have implementations for them in Python. So I just had to like copy paste them into Porth. Right. So, and the current size is 1064 lines of code. Right. So, and that's basically the current state. So here is the parsing of all of the intrinsics. Right, so here we have interpretation. The interpretation for some of them is not implemented because it may require like a simulating memory management, so, and I didn't come around to actually do that. But the simulation for the rest of the things is actually there. So you see we have a simulated stack and we're basically simulating these instructions, and also compilation for all of the intrinsics is pretty much there. Right, so here's the compilation, and all of that works actually. So all of that works. Which is pretty powerful. So for those who doesn't know, Porth is the programming language that I'm developing from time to time on this channel. I'm gonna give the link to the source code in the chat for people who just joined and for people who's watching on YouTube. I'm gonna put this thing in here, my programming language. which is not as cool as OCaml, of course, right? My language doesn't have OP, right? So, which makes OCaml even cooler than my language. Okay, so, yeah. What I want you to do, I want you to implement Hello World. If I remember correctly, you implement it like this. So you call functions in OCaml without any parentheses. So it's almost like Porth, but the other way around. You see? So in Porth, I would first put the string literal and then the function. In OCaml, I first put the function and then the string literal. So basically, it's pretty much the same thing. So... Alright, let's see if this thing is going to work. As far as I know, you can interpret a camel, right? So let's actually do all of that in the terminal. And let's go to this folder. So if you do OCaml main.ml, it will just straight up interpret this entire thing. Nothing particularly special, but OCaml has a compiler called OCaml-C, right? And what it does, it compiles OCaml into an executable, which you can run like so, and as you can see, it says hello world. But you know what's interesting is that you may think that, okay, it's a native executable, probably. But let's actually confirm, is that a native executable? It's a OCaml run script. This mother flipper, instead of generating a native code, just debated us and generated some sort of a freaking script. The fuck? Okay, let's take a look inside of this thing. That's a funky looking script, look at that. So essentially, it didn't really generate a script, it generated a bytecode. But here's the trick, it basically wrapped it into a shebang. So have you ever seen a bytecode binary with a shebang? Like, I don't know, like the only place where I saw this shit like that is in OCaml. Does anyone know anyone else doing this kind of trick? Right, because I've never seen it like anywhere except in OCaml. I mean, bytecode is fine, but it's just kind of an interesting idea. I mean, it works. It's actually 5-head. I do agree with that, but I would never think about doing it like that. So it's kind of cool. So it's a really big brain. Right, it kind of looks like a native executable and you can run it as an active executable, but it's not an ELF. It's not an ELF executable. It's actually like a shebang script. What's interesting is though, it doesn't mean that OCaml is incapable of doing native stuff. So for native stuff, it has a separate compiler called OCaml OPT, right? And if you try to use OCaml OPT, right, it will generate this thing again, and as you can see, this thing is a little bit beefier than it was before. Before it was 20 kilobytes, now it's actually 1 megabyte, so it generated shit ton of crap. And if we take a look at this file, right, if I take a look at it, not fike, I don't know what this fike even means. Yeah, so as you can see, it's a ELF 64-bit executable, and if you run it, it says hello world. So basically you have several options. You can use OCaml as a script, right? You can interpret it with OCaml. You can have a REPL as well. You can compile it down to bytecode, which is cross-platform, right? So you can have like a sort of like a JVM, right? JVM bytecode where you compile program once and run it everywhere. And also you can then compile the entire thing to native code if you need them speed, right? All right, thank you so much, Pawn Theory, for 5 months of Tier 1 subscription, and Ganovi Banane, I hope I pronounced your nickname correctly, thank you so much for 15 months of Tier 1 subscription. So, the real bangers, thank you so much for the real bangers. Okay, welcome everyone back to our epic OCaml club. So, okay, guys. So we managed to create a hello world. managed to create a hello world. So this is how a camel language looks like, essentially. So through a let, you define like sort of a binding, sort of a function, and this is an entry point, right? So, and you call functions like so. You define, you provide a function name and then the arguments like a, b, and c. And this is equivalent to f of A, B, and C in conventional languages. So this is how you do this, but in a camel, right? So first comes the function name, and then the separated by spaces the rest of the arguments. So this is basically how you call this function. So you may ask, how would you call something like this, right? So if you have like two nested functions composed together, how you call something like this? Well, in a camel you will have to do it like that, and then you'll have to wrap this thing in parentheses. So you still kind of use parentheses, but just to emphasize what is a function and what is not a function, you see? So that's basically the difference, like syntactical difference between the function calls of conventional languages, like a C-style languages, and languages from the family of ML, right? So, right, ML in that case doesn't stand for machine learning, it stands for meta language. So there's a whole family of languages where you call functions like this. Not like this, right? So, and one of such languages is also Haskell. In Haskell, you also call functions like this. Another one is a camel, so then SML, and so on and so forth. There is a whole family of functions like that, of languages like that. All right. So let's take a look at the problems that we need to solve, right? So we need to solve 99, not even 69, 99 OCaml problems. Okay, so what's the first problem? The first problem is working with list. Working with list is like a section. So all of the problems are split into 7 sections. Lists, arithmetics, logic and codes, binary trees, multi-way trees, graphs, miscellaneous problems, right? So we start with like working with lists. And lists is a fundamental data structure in OCaml, just like in Haskell or maybe in Lisp as well, right? So we need to write a function that is called last, and it accepts a list of elements A, right? So basically this is a generic list, and returns an optional A, right? It returns the last element of that list. And the reason is why it's optional is because if the list is empty, there is nothing to return, you should return none. Right, so, and this is how it should work. You call last on this list. As you can see, list is separated by semicolons, not commas, right? So it is needed to actually debate you and make a lot of compilation mistakes. And then if you, and this thing should return some D, where D is the last element of that list. And if you provide an empty list, it should return none. So that's basically what we need to implement. What kind of syntax is that, LMIO? Well, it is a different syntax, right? Different languages may have different syntaxes, right? So, in fact, there is nothing fundamentally correct or incorrect about the C-style syntax. It's just like something that was established historically. But you may have a different way of expressing things, right? So you not necessarily have to write things one way, you can write them the other way, right? So a syntactical thing is just like a color of the bike shed, it doesn't really matter. What's important in my opinion is the semantical difference. And semantical differences in OCaml, between OCaml and classical C languages are actually rather interesting. Syntax is just like something that you can quickly get used to. Usually when I look at the languages and I compare the languages, I rarely care about the syntax of the language, like I rarely care. For me, it's what's more important is the semantic of the language. In fact, this is one of the reasons why I'm not excited about Lisp as a lot of Lisp fans, because for me, Lisp is just a Python with S expressions, right? Since I don't care much about the syntax, I look at Lisp beyond its syntax, and beyond its syntax, Lisp is basically Python. So, especially Common Lisp, like it's just like straight up Python. Nothing particularly special about it. It's just like, yeah, you slap S expressions on top of Python, you get Lisp. So, yeah. But maybe there's something with my brain, right? So my brain does not find syntaxes of languages exciting or interesting because it's just like something that you slap on top of the language. It doesn't really matter. Valek Zero, thank you so much for a 26 month of tier 1 subscription. Thank you, and welcome to our Epic Camel Club. Okay, so how can we implement last? Right, so we're gonna have last, and this thing accepts a list of any elements, right? So this way you say that you have a list of A's, and A is sort of like a generic, right? So list of integers would be int list. List of floats would be float list. List of strings would be string list. List of any element, we don't care what that element is going to be prime A list. In fact, prime A is basically a generic. So basically this is equivalent to something like list of T, where, prime A is basically that T that you don't care about, right? So that's basically what it is, right? Prime A list is basically list of T, it's just like a generic list. And then you want to say that last is supposed to return a option, right? And that basically means that it will return like optional T, right? You have a function last, right? Function last that accepts list of T and returns optional T. So that's basically what it does. So it's just like an alternative syntax to that, right? An alternative syntax to that. That's what it is. So when the camel type variables come before the type, yeah. So if you have a type that is parameterized by another type, the parameter of that type comes before the parameterized type. So, Alrighty. So what we need to do? We need to pattern match access, right? If I remember correctly, you pattern match in a camel with match with. Right, so that way you can check, okay, so if the list that we've got is an empty list, right, if it's an empty list, we have to do something, right? So in case of an empty list, I already mentioned there's nothing to return, so we have to return none, if I remember correctly. So maybe this is incorrect code, but the compiler will tell us if something is wrong. Okay, so then we need to deconstruct the list. We need to deconstruct the list into its head, the first element, and its body. Maybe it's too late, actually. If you think about it, what's the most trivial case for the last function, right? So you need to implement the function that gets the last element. What's the simplest and the most trivial list from which it is obvious what is the last element? It's the list with a single element, right? If you have a list with a single element, the last element of that list is that element, right? So you just basically go ahead and just return X. It's pretty straightforward. It's the simplest case of like when you can just get the last element. All right, so and the general case is going to be when you have more than one element, right? So in that case, we can try to destructurize the list into its like head and the rest of the elements, right? So in this particular case, as you can see, like X is the head, and this is the rest of the elements, right? Since none of these patterns were like successfully matched, it will try to match this pattern. And how can we get the last element out of here? Right, so we know that there is more than one element in here, so that means the last one is not going to be this one. The first one is not the last one. So in that case, I can say, okay, well, let's just ignore that one. So, and the last element of that access list is going to be the same as the last element of the rest of the element without the head. Right, so that means we can do this entire thing recursively. And there we go. We implemented a function that finds the last element recursively, right? So we have a couple of bases of the recursion. In case of the no elements, you just return none. In case of a single element, it's a trivial case. It's the base of the recursion. We return that element. And when you have more elements, it's the same as last element of the list without the first one. And as you go, we have like a recursive process that basically chops off the element of the list list until it reaches the list of the single element, and it just returns that list to you. So here's the function. Is that clear? Does it make any sense? Hopefully that makes sense. Okay, so what we can do in here, I think we can try to maybe compile the entire thing. I forgot how to use OCaml actually. Okay, so here is an interesting thing. I'm trying to call last while being inside of last. And the compiler complains that it cannot find last. And this is because the functions by default in OCaml are not recursive, right? They are by default not recursive. So to indicate that a particular function is a recursive, you have to put a rec in here. And only then you would be able to compile your program if it has a recursive function. So this is very interesting. So all of the functions in OCaml, if you define them, you cannot call them recursively. And yeah, you have to specifically say that it's a recursive function. And I wonder why it is so. Maybe because the OCaml is one pass compiler, right? So until it actually has the whole function, it doesn't know its name. So you have to sort of like indicate that, like forward declare it or something. So it's kind of strange, but it is what it is, and it isn't what it isn't. So, right. So we have function last. Okay, I wonder if I can just like load some of the function in OCaml, right? So if I provide the OCaml repo, so it's going to be ML, and it doesn't allow me to just have a repo and load this entire thing. So I do remember that I had utop or something, but I don't quite remember. But anyway, so OCaml repo load file. I really don't remember how to load files into a repo of OCaml. Forgot how to do that. So okay, cut file. You can use that file. That's actually pretty cool. Okay. So if I do use and then I say main.ml, will that work? So I also have to put this double semicolon, and that kind of worked. And now I have last in my repo. So I can define a couple of things like 1, 2, 3. And there we go. So as you can see, we have, we have this list, and last return the last element. Right. So it's not particularly convenient, right? So OCaml by default does not define any functionality like a read line functionality, right? So we may want to use something like RL wrap. For those who doesn't know, by the way, so it's actually a very cool thing. If you have a program, right? If you have a program that by default doesn't have any history and doesn't allow you to like move around left and right with arrows, you can always just install a program called RL wrap, right? And it will automatically have a history and like everything that you get used to. So it automatically adds like read line functionality to your repo program that you have in here. So I think it's actually a pretty cool thing. RL wrap. So read line wrapper. Is that the official repo of this thing? I think. Well, it has a lot of stars, and it definitely deserves a star. If that's the official repo, it definitely deserves a star. And I suppose you can find it in here, but it's usually available in all of the like Linux distros that I used. So it's just like, yeah, it's available. And I'm gonna put that in the description for anyone who's watching right now. So RL wrap. There we go. So you can use this thing in here if you want to. Of course. Okay. So we've solved the first problem, believe it or not. We solved the first problem. We solved like last. And what's interesting is that since last is a generic function, we already discussed that it's a generic function. So you can use it not only with numbers, you can use it with strings, right? So you can do last and it will return you, well, we have to use this entire thing, so it has to be main.ml, there we go, and then I can just do something like this, and there we go. So it also works with strings, it works with any types because it's generic, right? So unlike some of the modern languages that are younger than a camel is actually a pretty old language. A camel does have generics. Right. I'm not going to point any fingers on any of the modern languages, right? But this thing has, you know, generics, and they work pretty fine. They work fine. Right. So, and again, if you use this thing on an empty list, right, it will return none. Okay. So this is the first problem. As far as I know, the comments in OCaml are kind of weird. This is the way you define comments, and as far as I know, there's only multi-line comments. There is no comments that comment a single line. OCaml has generics, but it doesn't have a single line comments, right? So there's always a trade-off. That's the price you have to pay, you know, to have generics, right? It's like with Python, right? So there's a trade-off. You can either have, you know, a newbie-friendly language or a fast language, right? In here, it's the same. You can only have generics or like single line comments, right? That's the price you have to pay. You cannot have both, right? It's impossible to have a fast and newbie-friendly language. It's literally impossible. Computer science haven't solved that. The same goes with, you know, single-line comments and generics, right? So these are mutually exclusive things. Okay, so this is going to be the problem 01, right? Problem 01. Cool. So maybe we're gonna actually just comment everything. So also Camel, one of the problems with the Camel is that it produces a lot of garbage, right? So every time you compile, it's just like CMI, CMO, CMX, ML. Well, ML is the garbage that I wrote. It's my garbage, like .o, a.out. So usually we want to actually kind of like, you know, git ignore all of that. So git ignore. So let me take a look at what we have in here. So first one is going to be, maybe I'm going to actually keep it like that. So git ignore, CMI, CMO, CMX, O, and usually we're not going to have a.o, so I'm going to just straight up like remove this entire thing. There we go, there we go. So are we going to have like some, I don't know, like quick start instructions? I don't think so. We're not going to have any quick start instructions because we don't have that many solutions anyway. Right, so let's do something like this. Solution for problem 01, and I'm going to push that right into the repo. And yet again, the source code is available right here, right now. You can find it in here. And for people who's watching on YouTube, you can find the source code in the description. So I keep track of what I'm going to put in the description. And hopefully I won't forget and won't lose this file when I'm about to upload this video. So that might happen. That actually happened a couple of times. I remember actually like keeping track of what I want to put in the description, and then I just deleted that file. And I don't remember what I wanted to put in the description. So if that will happen this time, I apologize. You can always Google all these links, right? So it's just like, yeah. Anyway, so what's going to be the next problem? What's going to be the next problem? We have 98 of them. We already solved one. Find the last but one, last and penultimate elements of list. Easy. Well, it's not really easy to understand, but okay. Oh, I suppose you need to return last and the one before last two. Okay, so that makes sense. All right, so it literally even called last two. Holy shit, the function itself is called last two. Problem 02. Okay, so this is going to be last two, and yet again it is going to accept a generic list, right? And I suppose it is going to accept return a pair of elements, right? So it's supposed to return a option. Oh, and I think I remember. So can I raise something like not implemented, or maybe like not implemented? Look, OCaml has exceptions, and you raise exceptions like in Python. It's literally like in Python, right? So majority of people believe that the syntax of the language equals to the language. So if some of the languages share keywords, that means they are basically the same languages. What is semantic? I've never heard of semantic. The fuck is semantic? The syntax. Syntax is the language. Syntax is the language. I bet Zozin could rewrite the port compiler in OCaml and that would be still faster than Python code. Yes, it would, because I actually worked with both big Python projects and big OCaml projects. And big OCaml projects are generally way faster than Python projects. Way faster, because, I mean, it compiles and optimizes to native code. Right. And in fact, it has a way better type system, so it catches more errors. But I mean, hey, at least it's newbie friendly, right? Anyway, so let me take a look. I don't remember how to actually do not implement it, but whatever. We might as well actually do something like assert false. Maybe that will work. So here's an interesting thing about tuples. Here's an interesting thing about tuples. You define tuples not like this, right? So this is a tuple type, right? This is a tuple type. This is a tuple with 2 elements. But, so this is the type. But the value of tuple, oh my god. The value of such tuple is actually going to be 1, 2. So this is how you define a type. Since this is 2 integers, let's actually define this thing as 2 integers. Okay, so this is the type and this is the value, right? And it makes it super easy to make a mistake and confuse them. And I remember multiple times actually defining a type like this and then trying to understand what the fuck is going on and why the compiler complains about that, when in reality you have to define it like this. And in fact, there is another pitfall in here. You don't have to even put parentheses around the tuples. Just using a comma is enough. And this is one of the reasons why lists in OCaml are separated by semicolons, not commas. Because this is not a list with 2 elements. It's a list with a single element, and that element being a tuple of 2 elements. A list with 2 elements, in fact, is something like this. So yeah, it is very freaking easy. If you're coming from a different language, it is very easy to make a mistake of defining a list like that and then still looking at the compilation errors thinking, where the fuck did I make a mistake, right? Because you're not defining a list with 2 elements, you're defining a list with 1 element, which is a tuple. So yeah, welcome to OCaml. So, it is what it is, and it isn't what it isn't. Anyway, but you get used to that quite quickly. So, it's just like Rust. It's like Rust. The language is not shit. You just have to get used to it. It is not shit. You just have to get used to it. Just like Rust. So, now, let's actually go ahead and implement this entire thing. So, yeah, I've explained all of that just to explain what the fuck is going on here. Okay, so this time we actually have a couple of different cases. So in case of the empty list, we have to return none. In case of a single element, we also have to return none. I wonder if we can sort of collapse these two branches. Maybe not. I don't know. But in case of 2 elements, right? In case of 2 elements, you have to return those elements. So it's going to be sum x and y. There we go. So, and then what we have to do, we have to repeat this iterative process, right? We're gonna destructure the list into the rest of the element, and last 2 of that list is basically last 2 of the rest, right? Last two of the rest, and this thing has to be recursive. There you go. It's pretty much the same solution, except we have additional case, right? How would you do 3 elements tuple? You would do it like this, like so. Okay, so let's see if this entire thing compile. I'm going to try to compile, and this thing returns none. I suppose I have to actually put parentheses in here, because, okay, so there is a difference. There is a difference between this and this. This is a tuple where the first element is A, and the second element is optional A. If you need an optional that contains a tuple of A's, you have to do it like that. You have to be careful with the order of things that you define, right? Because this thing is not the same as the one with the parentheses, right? So this is like a tuple with 2 different elements. First one is not optional, and the second one is optional. Right. So, okay. I always wonder the language creators' reasoning behind syntax choices. Well, a camel comes primarily from academic environment, and academic environment is usually quite isolated from the industry, and they don't care about the conventions of the industry, and that's the reason why you sometimes see the languages like that. So yeah. Right. Because people in academia don't even know that somebody programs for for money and for other people. They think that programming is just like a branch of mathematics, right? So for academic people, it's just yet another branch of mathematics. It's just, yeah. And everything in academia, there is everything there is to programming, and there is nothing outside of academia in terms of programming. So that's why you end up with conventions and languages like that. So yeah, it's just another branch of mathematics, right? Just applied mathematicians, nothing special. Anyways, I think we solved this thing, right? Didn't we? Can I reuse the same file and redefine some of the things? I wonder. I can. So I can stay in my repo and I can just update this function and just can reload them and stuff like that. Can I just reload or something like that? Unknown directive reload. Did you mean load? Maybe. Did I mean load? I don't even know what is load in terms of like a camel repo. I know a thing or two about a camel, but I know almost nothing about a camel repo, which is kind of strange. Which is kind of sus, not gonna even lie. So if I try to do, okay, do we have help? Do we have help? We do have help. Would you look at that? So apparently we have some shit in here. So we have help. We have quit. You can quit through the pound. You can do cd, change the current working directory, add the given directory to search path for source and compiled files, load in memory a bytecode object produced by C. So you can load recursively things, you can remove directories and stuff, read, compile, and execute source files, show, print the signature of the components of any categories below, show class, show exception. That's pretty cool. Okay, so I didn't know that you have so many epic things. By the way, even though a camel comes from academia, right now in 2021, as far as I know, it's used as an industrial language, right? So it's used quite actively in an industry, and the biggest user of a camel, as far as I know, is a Jane Street company, right? I think that's the biggest user of a camel. Does anyone know about this company? Right, so it's basically a trading company, and so one of these sort of like one of the feature of that company is that they're using a camel there for everything. It's just like the main language of this company, like everything is in a camel. Yep. So I suppose a lot of people know about Jane Street if they're mathematicians and maybe watch some mathematical content on YouTube, like, you know, stand-up math or 3 Blue 1 Brown, because as far as I know, the math YouTubers actually partner quite often with Jane Street, and they're sponsored by them to promote them as the workplace for potential like students, like something like that. So yeah, I'm gonna leave the link to the Jane Street in the description for anyone who's interested, so I'm gonna put them in here. I'm too stupid to work in there, unfortunately. So yeah, but it's I heard it's a cool company, Jane Street. There we go. So all right, so what I want you to do, I want you to test last two, right? So let's test last two. If I have something like 1, 2, 3, 4, right? It returns last two elements in here. And if you have a single element in here, it's supposed to return none. And if you have an empty list, it also returns none. So we basically solved the second problem. Isn't that cool? Isn't that cool? I think it's pretty freaking cool, mate. Okay, then. So, yes, sir. Okay. Add solution to problem 02, and I'm gonna push that right into the repo. Okay, so what's the next problem? So we have 97 problems to go. Find the kth element of a list. Easy. Okay, so you have to define a function at, which accepts the number and the list and returns you the nth element of that list. So in our case 3, it will return 1, 2, oh, it even starts with 1. Okay. Remark, a camel has list nth, which numbers elements from 0 and raises an exception if the index is out of bounds. Right. So, and so people, to make people not use nth as a solution, this thing doesn't raise exception and also starts with 1. Disgusting. Anyway, let's go ahead and implement this thing. Okay, so we need to implement at. So as you can see, it accepts integer k and list of a's, and it's supposed to return optional a. Right, there we go. So we have to implement this thing. I wonder if you provide 0, I suppose it also should return like none. So we have like a couple of situations, like if k is, oh boy, oh boy, oh boy, where is my soy? I guess we could match axes like so, right? You can match axes like so, and in here you're gonna have x and rest. If I remember correctly, on top of having the parents in parent match construction, you can have like guards, right? So here is the pattern, and there's also additional condition, and I think it's something like that. So when x has this particular pattern, and when k is equal to 1, then you can safely return return x. But I don't remember for sure, right? So I want to actually Google it up. A camel, pattern, matching, and I think they're called guards. Guards, it's like mods. Oh yeah, there we go. So you can have a pattern, and then you can have when with condition. It's pretty cool. It's pretty cool. Okay, so if we have just something else, well, I mean, we have several situations, right? When k is less than 0, right? When k is less than 0 and when k is greater than 1, in all of those cases, we want to actually go to different places, right? So, right. So in case of k like less than 1, this is a straight up none, right? Because you cannot go less than 1. You cannot go less than 1. But if it's greater, you wanna actually recur. You want to actually recur. So in case of this thing, if it's greater than 1, you want to do something like at k minus 1 rest. There we go. So, and if you end up with an empty list for whatever reason, right? So with an empty list, this is also none, essentially. So can we simplify this entire thing? We could probably move all of these conditions inside of this branch, but I don't know. Is rest a special match word? No, it is not actually. It's just like, it's just a name for a variable, right? So basically I'm bounding the first element of access to x, and the rest of the elements except x to word rest. I can call it something like wise, and it's going to be the same. What's interesting is that in here, we don't really care about rest, so I can do something like this, right? So, yep. If k is 1 and you have like at least one element in here, you can return that element. If for whatever reason k is less than 1, you have to return none. Interestingly enough, maybe we can even remove this case and just put something like this in here, and I think that will work. Yeah, this is actually greatly simplifies the situation, right? So if you have at least one element k is equal to 1, the result is that element. If you have more than one element but the k is greater than 1, you recur with k minus 1 and the rest of the element. If your list is empty or k is less than 0, well, in that case it's just like a straight up none. There's nothing to do in here. There's nothing to do in here. That is very interesting, actually. It seems you totally ignore what I'm telling you. Well, here's the thing. Mr. Botka is the bot of this channel, so it does in fact ignore everything you say because it's a bot. I'm really sorry to tell you that, but I think, like, I don't like to be that guy. But I think you need to know that Mr. Botka is a bot. All right, so let's see. Let's see. Is it going to work? Can I actually just like do use? Yep. And it seems to be working. So let's take a look at some of these test cases in here. 99 problems. I might as well just like do that, and this thing should return sum C, and as you can see it returns a sum C. If we're gonna do something like this, it returns none. And furthermore, if I try to do 0, it also returns none, right? So that makes sense. But if you do 1, it returns sum A. I think this is a reasonable solution for this problem. What do you guys think? Right. I think this is in fact a reasonable solution. Maybe you can compress it even further, right? But it's fine. It's fine. All right, so this is a problem, problem 03. Problem 03, and let's go ahead and just commit that. Add solution for problem 03, and we're going to push that right into the repo. So what's going to be the next problem? So far so good. So far we only have easy problems, and as far as I know there's also medium problems, and the first medium problem is flattened nested list structure. It's actually not that much difficult than the previous values. What is the first hard problem? Huffman code. That's quite of a jump. I mean, okay, between flattening the structure and Huffman codes, I mean, Huffman codes are not that hard, but between flattening the structure and implementing Huffman codes, there's quite a bit of a gap. It's not as much of a gap as between easy and medium. I'm not quite sure. And actually, the first hard problem is actually 50th one. So, to be fair, I planned to implement Huffman codes as a separate stream topic, actually. So So it will be interesting. I don't know if we're gonna actually get the 50th problem. It's a halfway through. But Huffman codes are actually very interesting. I remember implementing them when I was a student, and they're really, really fucking fun. So the idea of Huffman codes is like, essentially you have a sequence like of bits, and the most common sequence of bits should be represented with the shortest sequence of bits, and basically you build that substitution based on the statistics of this sequence of bit, and you do that with a tree or something. Yeah, I think I quite remember, like roughly remember, so I probably need to read on Huffman codes a little bit more, but they're quite like they're usually used for compressing stuff. Huffman code is small on the camel. Ah, okay. So maybe that's why they put it in there, because maybe the functional approach works really well with Huffman codes. Okay, so what's going to be the next problem, right? What's going to be the next problem? The next problem is going to be something like a problem 04. Problem 04. Find the number of elements of a list. Easy. Okay, OCaml standard library has list length, but we ask you that you re-implement it. Bonus for a tail recursive solution. Ooh, who knows what is a tail recursion? Tail recursion. Under tail recursion. So let's go ahead and try to do that. So this is going to be like a length. And in here, we're going to accept the list, right? And this entire thing is going to return an integer. Okay. How would you implement the such function? Right. So let's go with the recursive approach yet again. We're going to match access, right? And what's the simplest case? What's the simplest list, the length of which you can calculate easily? Let's put it this way. I suppose it's an empty list, right? So if you have an empty list, you can straight up say that the length of that list is 0. Right. If you have a list where you have more than one element, right? So the length of such list is going to be the length of the list without the first element plus 1. There you go. We implemented a very simple function that calculates the length of the list recursively. So let's actually do use, and it doesn't compile yet again because you have to mark this function as recursive, right? So, and let's do length, and I'm going to provide the empty list. It is 0, 1, 2, well, I'm sorry, 3, and so on and so forth. Right, so, but they also promised extra bonus for tail recursive solution. Who knows what is a tail recursion and how you can implement this thing tail recursively? Who knows what it is? So they even provide the link to a Wikipedia article about tail call. So let's actually read about it. So I don't know what is a tail call, right? In computer science, a tail call is a subroutine call performed as the final action of a procedure. If the target of a tail is the same subroutine, the subroutine is said to be tail recursive, which is a special case of direct recursion. Tail recursion or tail end recursion is particularly useful and often easy to handle optimization in implementations. Thank you, Wikipedia. Very cool. This is a very clear description of a tail call, tail recursion, tail end optimization, whatever the fuck you want to call it. It's just the only important rule in here is just to have word tail in it, right? So you have to use words tail and call recursion in any order you want, right? And it will mean something. Tail recursion isn't even in Perth. Why would we need to know? That's a good question. We could probably implement it. Yeah, GPT-3 text LMAO. Yeah, exactly. So it feels like it's generated by GPT. Like, what the fuck is it? Like, is this shit? So maybe if we read a little bit further, maybe we'll know what the fuck it is. Tail calls can be implemented without adding a new stack frame to the call stack. Oh. Most of the frame of the current procedure is no longer needed and can be replaced by the frame of the tail call modified as appropriate, similar to overlay for processes but for function calls. Yeah, this is already a little bit closer to what it is, right? Just a little bit closer. Okay, so let's actually maybe take a look at a simple example like in C, right? So I would like to use C because it's more of a like a lower level language. It's closer to the hardware and it's closer to what actually is happening, you know, on a hardware level. Because tail call and tail recursion, it's more about low level thing, right? It's more about low level thing. So you have something like this. I'm going to explain what is a tail recursion and tail call optimization from my point of view. I'm very dumb person and I'm very uneducated, so I may not know some things. I'm sorry, I don't have a PhD in computer science, so I'm going to get some of the academic terms wrong and I'm going to upset a lot of, you know, PhD researchers. I'm really sorry about that. I'm going to just say how I understand this kind of shit. Okay, so let me see. So imagine you have a function that looks like this, right? So you accept an integer and you return an integer, right? If x is less or equal than 0, right, you're going to return 0. Otherwise, you're going to return maybe 1 plus f(x), right? 1 plus fx. So what happens when you call such function, or in fact any function, right? On a low level, we have so-called call stack, right? It's a small region of memory, usually on architectures such as x86-64. It is starting from one place and it grows towards, you know, 0 address. Maybe we want to actually draw this kind of thing a little bit. So something is wrong in here. Okay, so let's imagine that we have a memory, right? So here is the memory. Here's the memory. It's more of like a virtual address space. So you have a stack that starts in the memory somewhere here. So this is a stack. As you push more elements onto the stack, they're pushed towards 0. So 0 is located here, and the you know, memory addresses grow towards like right side. So a new element will be pushed like this. Right. And on x86-64 specifically, the end of the stack is kept tracked in the RSP register. So you have a RSP register, it points at the top of the stack, which grows towards 0 for whatever reason. It's x86-64, right? So essentially, when you perform a function call, so how an argument of a function is passed to the body of the function. So I don't remember specific details, but if I remember correctly, the call instruction will push the return address on the stack, right? It will push the return address on the stack. So it knows where to return when you do the return, right? And it also pushes that x in here. There we go. So, and of course, that kind of like modifies RSP. There's also RBP, which is, you know, like a base of the frame and stack frames. We're not going to actually go in like that deep into the stack frames. We're going to only talk about RSP and stuff like that. Right. So here are the things. And when you're referring to like X, you're referring to that X on the stack. It was passed from Y to U via the stack. So recursively, when you call f yet again, you need to push. I forgot to do this thing. I think I forgot to do -1, right? Yeah. So you need to push another frame. So you call f yet again recursively, right? You call it yet again recursively. So that means it will push its return address yet again on the stack and then x -1. And it will keep pushing elements until it will reach this situation. and it will start returning from this recursion by popping all of this element and returning back from the return addresses. So basically, as you go deeper and deeper into recursion, it will push more and more things onto the stack, and then when it's time to return from the recursion, it will pop everything and return the results. That's basically what happens on the low level, on the machine level, when you program a recursion. And that's why I'm using C to sort of demonstrate that. Does it make sense, right? So this is usually what we call a call stack, and this is how it's usually used, right? Without the call stack, you would be able to do like recursive in the classical sense that we do. Okay, here's an interesting thing. Now let's take a look at the function that looks like this. That looks like this, right? So essentially, we have just X on the stack and a return address. And then we call this function again, but then we don't really need the result of this function up until we completely return from it, right? So in that case, we probably want to maybe assign it to a variable, right? So we keep calling function to itself, but it will only push the same thing over and over on the stack. So in this particular situation, one of the optimizations that you can do, you can basically not push this pair of elements over and over again, and basically reuse this pair for the next F call, right? So basically tail call optimization is basically not pushing yet another pair of this element, this stack frame, but simply reusing it and decrementing X in place on the stack. That way the stack is never gonna grow, and you can only achieve it when your function looks like this. When the last call, when the call to the function, recursive call to the function is the last one, and it's never, like the result of it never used except like returning. So when you have situation like this, it's quite easy for the compiler to optimize everything and just not push additional frame and just reuse the same one over and over again. So this is basically what I understand when I read about tail call optimization and like tail recursion and stuff like that, but I might be wrong. But if you read the description one more time, tail calls can be implemented without adding a new stack frame, exactly as I said, to the call stack. Most of the frame of the current procedure is no longer needed and can be replaced by the frame of the tail call modified as appropriate. So as you can see, as I already said, you have a single frame, and on each call, instead of pushing a new frame, you just keep modifying the current frame, basically turning recursion into loop. Does it make sense? So this is how at least I understand it. But again, I probably got some terms wrong, I probably get some details wrong, and that's why I don't have a PhD, right? That's why I'm labeled as a dum-dum, right? So, yeah. So does anyone have a PhD in computer science in the chat? Please correct me if I'm wrong. So where did I make mistakes in here? So this is how I understand it. And so functional programming people really like tail call optimization because it makes their slow languages look good in some certain situations, in some certain circumstances, right? Because usually functional programming languages on average are slow for real world problems, and that upsets functional programmers, because, you know, programmers in 2021 are like sports fan. They're like they're rooting for their team, and they get very upset when their team is not doing well. And functional programmers basically found a way to make their team look good in some certain circumstances. That's why they like tail call optimization, right? So yeah, because it allows them to optimize slow recursion that pushes a lot of stack frames on the stack and turn it into a loop, right? And they ask us to rewrite the length function in a tail recursive fashion, right? So that's basically what they ask us to do, right? So right now, this thing is not tail recursive, right? Because calling to length is not the last thing in this entire implementation. So for this function needs to wait until the call is done so it can add 1 to the result of that call. And so because of the necessity to wait for the results of the lower call, you need to use the stack, right? So you need to use the stack in here. So to make this entire thing tail recursive, you need to turn this thing into this thing somehow. You need to somehow make this function look like this, but then it needs to compute the size of the list. Well, the usual trick in function programming of turning a recursive not tail call optimized function into tail call optimized one is to use so-called accumulator. There is an accumulator trick, accumulator technique. And once you learn that accumulator trick, accumulator technique, you can basically apply it pretty much to any sort of iterative recursive function to turn it into tail call function, so then it can be optimized by the compiler, and who needs imperative languages after that, right? So who needs imperative languages, am I right? All right, so let's actually go ahead and just implement this entire shit. So usually it is implemented like this, right? Length, let's call it like a tail, right? So essentially you accept the list, the first thing. And the second thing you accept is an accumulator. So an accumulator is going to store the final result. So it's basically the result. Maybe we're going to even call it the result. So the result becomes the input parameter for the function. So the result becomes the input parameter for the function. Okay, so then we match access. If we encounter an empty list, we don't return 0. We return the result. We return the result. If we encounter the list that is not empty, we call length tail again without the head, but with the result incremented by 1. And there we go. We achieved what we wanted to achieve. So now this function is tail called, right? So basically the recursive call to the function is basically the last thing that you need to do. And the result is carried through the arguments of the function, right? So the result is not returned, but sort of carried through each individual call. And this is something that the compiler can finally optimize and not push stack frames. You see? So that's a tail call optimized function. And the way you call this function, right? The way you call it, so let's actually use something like use. There we go. So this is going to be length tail. You have to provide 1, 2, 3, and you have to provide the initial value for the result, right? So in case of an empty list, it has to be 0. So that means the initial value for the result has to be 0. And there we go. As you can see, we have 3 elements in here. So if you have 2 elements, it's going to be 2. If the list is empty, it's going to be 0, right? So, but it's not really convenient to have this extra element. So what usually functional programmers do, they sort of like tuck the this function under another function that basically provides that that default element for the result. So let's actually call this thing length tail prime. And let's wrap it into length tail, which accepts only the list, right? It accepts only the list. And this one becomes the inner function that we just call with the default parameter 0. So you see, in a camel, you can actually quite easily define nested function, and this function is not going to be visible like outside of this one, right? So the syntax of a camel is quite ergonomic in that case, because the inner function syntactically is not that different from the outer function, and you just can quite easily wrap everything. Right. So let's do use, and as you can see, everything works, and I can do now length tail 2, 3, 4, and there we go. So it works. But like, there's no difference between like it's kind of difficult to observe the actual difference between like tail recursive function and not tail recursive function because they behave the same, right? So the implementations are slightly different, but they behave the same. And do we really improve anything? Did we really improve anything? Did we? I don't know. We can try to check that. Let's actually write a useless recursive function, like a useless iterative function. Something like f, right? Which essentially returns an integer. And what it does, it basically calls to itself, but it increments its result over and over again. So essentially, for this function to work, it needs to push things on the stack. And since it doesn't have the base, it's gonna go into recursion indefinitely. And since it's not tail recursive optimized, it will Stack Overflow. Right? Not everybody knows in 2021, but Stack Overflow is not a website. It's not only a website, but it's also an error that you can encounter if you're not careful with the recursion, right? So, I'm sorry. Yeah, let's actually try to see what's going to happen if we call this function. It doesn't even compile. Okay, so because I forgot to mark it as a recursive one. So, all right, so if I call this function and a boom, Stack Overflow during evaluation. Looping recursion. I really like how it asks the question. Looping recursion? Oh, I see what you did there, buddy. Oh, looping recursion. Okay, so how can we make it, you know, tail recursive, right? So this is going to be ftail, and this thing is going to accept an integer instead, like result, right? And what it's going to do, it's going to just call itself, but with the result incremented by 1. As you can see here, we carry the result y the return, but here we carry the result y the argument, right? So, but since this thing is the last thing that we call, it will be optimized and won't push any stack frames. And since it won't push any stack frames, it's basically going to loop forever and never going to Stack Overflow, right? So let's actually do something like use, and I'm going to do ftail 0. And it's just hanging, it's just looping. It's a recursive function that keeps looping and doesn't Stack Overflow. So we can clearly observe that one function pushes the frame on the stack, and that's why it Stack Overflows, and another one doesn't push. So this is how you can demonstrate the difference between these functions. Hash trace allows you to see the behavior of the function. I didn't know that. Let's actually take a look at that. So can I do something like help trace or whatever the fuck it is? I don't know. Okay, so trace foo. I don't know how to use this function, I'm sorry. But I'm gonna read how to use it a little bit later. But anyway, we can actually observe the difference between the behavior just like that, right? So one function overflows the stack and another one doesn't overflow the stack. And this is something that you can use even in not function languages. As far as I know, some of the C compilers also can perform tail call optimization. So let's actually see. Let's actually try to apply the same trick in here. Right. So if we have something like this, 1 plus f. This entire thing is definitely going to Stack Overflow, right? So it's 100% is going to Stack Overflow. If I do gcc, you know, main.c, and then I'm gonna just run this entire stuff. So we got a bunch of gifted sub from the Bone Hunter. Thank you so much, the Bone Hunter, for 5 tier 1 subs, and everyone who got the subs, welcome to our Epic Tail Recursive Club. How about it? I don't know what the fuck is going on with me. I think I drank too much tea. So how are you guys doing? How are you guys doing? You're welcome. Thank you. Thank you so much. Really appreciate it. Just want you to say that your parser combinator in OCaml is pretty fun to use. Somebody using it? You're actually using it? Yeah, some time ago I implemented a parser combinator in OCaml. I don't remember. Parser parkour. I forgot that I call it like that. It's like parsec combinator of monad and parcoom. So, okay. So my sense of humor didn't change apparently over the years.
I like camelos.
Thank you. Is that a donation? Just a second. I didn't expect. The Extra Genius subscribed with Twitch Prime saying, I like camels. I also like camels. They're pretty cool. And that's why I program in Perl. Thank you so much for the sub. So yeah, you can find this thing in here if you're interested, and I'm also gonna put it in the description. I think I also did it on the stream some time ago. Right. So parsec combinators of monad in a camel. So it's actually a very simple one, right? It's not as generic as a lot of parsec combinators in Haskell, right? Because if you take at something like parsec, if I remember correctly, so where's the package? Where is my package? Parcoom, src parcoom.ml. So this parsec combinator, you can only parameterize the result, right? So the input is always the string with position, and the output is always the result and like the rest of the string and so on and so forth. So the only thing you can customize in here is the result, right? But if you take a look at something like parsec, right, parsec, arctum.
Решетка trace, name of the function, allows you to follow the behavior of functions, has a special behavior for tail recursive functions.
Okay, thank you so much for 500 bits. Let's give it a try. So I just have to do it like that. Name of the function. Okay, it's just the name of the function. Is now traced, and then I just call this function. Okay, and it's just like keeps looping, and I can't stop it. Okay, it's stopped. Well, it's not tail recursive. Okay, so if we trace tail recursive one, right, and it's going to be tail 0, and it even shows the arguments. Okay, that's actually pretty cool. Okay. Oh, I know why it takes so much time, because when you control C, it rises the exception, and exception needs to go through the entire thing. Oh, it keeps printing. Oh my god. That makes sense. It's just basically printing like everything that, yeah. So it's basically the stack trace, since it's a recursive. Okay, that's actually pretty cool. Thank you so much, Arctum. I didn't know about that, so that's very, very useful. I'm gonna use that from now on. Thank you. All right, so what I want you to say is that in case of a parsec, all right, in case of a parsec, if you take a look at the parsec combinator that they defined, you can customize pretty much everything, like every aspect of the parsec combinator, right? So if you take a look at the definition, right? So you can customize not only the return, right, A, you can customize the monad that is going to be used, right? In case of Parcoom, the only monad you're allowed to use is result, but if you want to have a different monad, well, you cannot do that. In Parsec, you can do that. You can customize the input, the output, and so on and so forth. And that's why it's so complicated. It has a lot of like these weird things, like it's super generic, super like customizable and stuff like that. My Parsec combinator, you cannot do that. That's why it's so small, so simple, and probably so fun to use, because it's not particularly customizable, right? But this is like a trade-offs that you have to take, because it's kind of difficult to make such a generic thing in a camel without like type classes and stuff like that. But yeah, so I cut a couple of corners to implement this thing in the camel. All right, so let me see. So we wanted to see if the C compiler actually optimizes anything in terms of like a tail recursion, right? So here is the not tail recursive function. Let's see if it is going to you know, a Stack Overflow. Main.c, this is going to be main. Yeah, segmentation fault. So I would assume that segmentation fault will mean the Stack Overflow. So maybe it would be nicer to do that with Clank, and Clank sanitize memory flag. Right, fsanitize memory. So I suppose it will tell me that with Stack Overflow, if I provide this flag, hopefully it will tell me. So there we go. So Stack Overflow. So now we can like clearly see that it's Stack Overflow. So if I turn it into sort of like a tail recursive one, so here's the result, and the result is going to be simply +1. Right, so this is going to be 0, and let's try to run this entire thing. And as you can see, this Stack Overflow as well. So the compiler didn't optimize anything. But the question is, what if we crank up optimization to 03? Will it do a tail call optimization? What's interesting is that it basically illuminated the entire thing. Thank you, Clank. Very cool. So it's supposed to actually hang, but it didn't hang because you never used the result of this thing, so it just eliminated the call. Like, I mean, it turned into a lazy language, right? It straight up turned C into Haskell, because this is what would happen in Haskell, right? You don't use the result of the function, well, it will never be called. Right, pretty cool. Thank you so much. So you don't need GHC to have Haskell. So we can try to print the result of this thing to sort of force the compiler to not illuminate the entire stuff. And it printed something. That's what's interesting about it. It actually managed to print something. Thank you, Clank. Very cool. So yeah, very cool. Clong is sus. Yeah, I mean, we actually did 03, which is like very aggressive optimizations, but I guess in these kind of situations, the optimization is too aggressive. Is it different every time? Yeah, it is different. So it's probably printing like a random garbage from the stack, I would presume. So maybe that's what it's doing. God bolt. So let's take a look at what kind of garbage did it generate this time. Okay. So Clang. I don't know what's my version of Clang, to be fair. So maybe I'm gonna just choose like the latest one or whatnot. So what is it doing? LDR push. Oh, it's ARM. Holy shit. Okay, so I'm an idiot. Or maybe God Bolt is not as convenient as it should be. Maybe it's not me who's an idiot. Oh, very cool. Okay, so in main we jump back to here. Well, we're supposed to loop, right? So let's maybe use the Clang that I have. This is not how you do version. This is not how you do version. 701, right? I have a pretty old one because I'm on Debian. Now that looks like something. Okay, so we're pushing Rex EDE. Okay, so this is the string. We're pushing the string. Oh yeah. So essentially, it prints. So the second argument, as far as now, is RSA, right? So x86-64, like system v call convention. So we get a rate from Provot. Thank you so much for the rate. How was your stream? We're just doing some weird shit. So as far as I know, it's first RDI and then RSI, right? So what's the second argument? Does anyone remember? What's the second one? But I suppose the second one is not even present there. So basically it will print a random garbage from the second argument register. So that's basically what it optimized to. Is this for Porth? No, it is not for Porth. We're just exploring how C compiler may potentially perform tail call optimization. That's what we're doing right now. So we were just discussing the tail call optimization, and we just want to see if any of the compilers actually perform them. So we did this thing, and what's interesting is that Clang Clang specifically of the version 7.0, with 0.3, it eliminated this call completely. It eliminated this call completely, but it didn't eliminate printf. So basically it's printing a random garbage from, I would presume, RSI. Right, so the first argument is RDI, the second one is supposed to be RSI, but RSI is never set anywhere because setting RSI, I presume, was eliminated. So, nice one, Clang. Thank you very much. Isn't the code an infinite loop? Yes, that's the point. And I would expect it to actually loop indefinitely, but the infinite loop was eliminated. And now printf just prints a random garbage from the registers. So LLVM is so smart. Well, in defense of LLVM and Clang, we're using a pretty old version of the compiler, right? Because that's the version on my old Debian machine. So the latest one actually produces something more reasonable, right? So the latest one produces straight up infinite loop. So it's jump to itself, which is precisely what I meant here. Believe it or not, it even eliminated printf. The 7th version eliminated the loop but didn't eliminate printf. The latest one eliminates printf but didn't eliminate the loop. And so this is closer to what I actually meant in here, right? So it's closer to my original intentions. Can you show 01 on which compiler? On the old one or a new one? So let's take a look at the old one. So this one, 02. 02 is the same shit. 01. 01 will probably... 0. What about 0? 0 now produces something reasonable. Like, I mean, it just didn't apply any optimization, so it's just like straight up. So anyway, we just were talking about tail call optimizations because we were doing a functional programming. Boys and girls, we're not programming in C right now, we're programming this. People who came from Prot, who knows what this language is? So new people who came from Prot, what is this language? OCaml, somebody knows this language, yes. And what we're doing right now, we're solving 99 OCaml problems. So that's the topic of today's stream. It's not SML, it's OCaml actually. Right, so the Godbolt thingy was just basically a tangent. The main the main topic of today is actually, you know, solving 69 OCaml problems. You can find the source code of the solutions in here. All right, so oh yeah, that's pretty cool. Okay, so we looked at two different solutions, right? The first solution is recursive one, and the second one is a tail recursive one. But not a single function programmer will talk about the third solution. Who knows the third solution? Not everybody knows. Well, I mean, functional programmers know about that, but will never tell you. But in OCaml, you can have, I think, while loops, right? Loop and recursion. I think, do you have while loops or for loops? Looping over lists. I think there's only 4 loops in here, right? So if I try to do something like while, there is a while. Okay, so let's actually call this best length, right? So this is going to be access, list, and this thing is going to be like this. Right, one thing in OCaml is that even though it's completely immutable and completely functional and so on and so forth, you can define mutable variables in there, right? So you can define variable result, and it's defined through a feature called the ref, right? So you define the ref 0, right? Then you can have your list defined also in the ref, right? So, and one of the things you can do, you can basically have an imperative loop that basically loops while the list is not empty and imperatively increments the result and then just returns the result when it's done. So this is the third solution that not a single functional programmer will tell you about, but I'm gonna tell you because I'm not a functional programmer, I'm a Python developer, right? So I'm gonna tell you that little secret that you can do this kind of stuff in OCaml. But I forgot how to use while loops. Okay, so this is how you do that. You do while true, do, blah, blah, blah. So if I remember correctly, to read a value from a ref, you actually use exclamation mark and you sort of dereference it. So you basically read this entire thing. And then you can check if this entire thing is equal to an empty list. While this thing is not an empty list, do result equal result plus 1. And then wise equal wise list, I think tail, right, list tail, and then done. There we go. And after that, you simply return whatever you have in the result. So this is the third secret solution that nobody except me will tell you. I wonder if it will compile, actually, we'll see. Okay. So use, and it does not even compile. Oh yeah, because you have to, if you have like a, you know, imperative statements, if you have imperative statements, you have to separate them with semicolons, right? You have to separate them with the semicolons. There we go. So if I use now best length, right, if I use best length, 1, 2, 3, it also works. It also works. So this is the best way to compute the length of the list in OCaml. This is the best one. So, all right, let's do a committee. And maybe even pushy. Add solution to problem 04, and I'm going to push that right into the repo, and the repo is public. You can find it in here, and if you're watching on YouTube, you can find the repo in the description. It's the first link in the description. So, okay. So, reverse list. This one is interesting. How do you even reverse a list? Well, you can use while. Oh my god, I just got a perfect idea. Holy shit. Here's an idea. Solve all of the 99 OCaml problems in OCaml in imperative style using mutable variables, for loops, and while loops. And just like promote that shit on all of the social media to piss off all of the functional programmers. That's beautiful. I want to do that now. Holy shit, I want to solve all of them in imperative style in OCaml. Yes! That's actually so cool. I want to do that. I don't know. I'm too tired, to be fair. I'm kind of too tired for this kind of shit. Too old. I already have enough people telling me that I'm programming things wrong, so... Alright. Problem 05. Problem 05. So I think... Oh, what's cool is that you can kind of reverse the list by doing the accumulator thingy, I think. Because once you push into accumulator, you sort of push things in a reversed order. Right, so let's go ahead and do that. And maybe this is going to be the last problem because I'm feeling a little bit tired already. So yeah, let's do this as a last problem, and then we're going to wrap things up. And I'm going to think about, you know, 99 OCaml problems, but imperative style. And by the way, so maybe I can even stream that, because imperative OCaml is easier for people to understand than the functional one, right? Because it's just, yeah, it's just like Python. It looks kind of like Python. So, okay. So this is the list. It's actually a list. And we can have something like an accumulator, right? So it's going to be like that, and then we're going to return this list. So we're going to match axis, and if axis is empty, we're just returning the accumulator. If it's not empty, right, we do a reverse, where we provide the rest, but we append x to the accumulator. So here is the thing. So essentially, how do we work with all of that? I wonder if I can just use... I think I can use tracing to demonstrate how this entire thing works. So yeah, thank you so much, Arctoon, for teaching me about trace, because I think I would be able to use it to demonstrate how this reversing is actually works. Because what it does, it chops off the head of the axis and pushes it into the accumulator on each iteration. So basically, like push and pop and push and pop, push and pop, and that's why it like reverses. It's like having two stacks. If you pop from one stack and push to another one, the second stack will be reversed version of the first one, right? So, and this is basically the same situation. And I wonder if I can actually demonstrate that with a trace. So let's gonna do use. And of course, I forgot to mark this entire thing as a recursive one. Use one more time. And if I try to reverse 1, 2, 3, 4, 5, it will... oh yeah, I forgot to actually provide the empty list. There we go. So as you can see, the result is actually reversed. But the way it works, right, like Towers of Hanoi, yeah, it's kind of like Towers of Hanoi. So essentially you have two towers in here. The first one is an input, and the second one is an accumulator, right? So we just like push into another one. Can we try to do trace rev? Right, so rev is now traced, and if I do 1, 2, 3, 4, 5. Oh, yeah, of course. Okay, so poly doesn't really tell me much. Okay, it's very cool. Roly poly wants a crack. And it's cool. We can try to maybe, is this because it's curried? Probably. Ah, this is the special behavior. Oh, okay, I see. What if we make it uncurried? So can we try, well, in case of making it uncurried, will it be still, yeah, it will be still like recursive or something. Okay, so we can try to do that. So it's going to be axis, and we're going to just do it like that, right? So if I try to do it like that, will it give me more information about this thing? Probably not. It's just probably not. And then if I do reverse, this is going to be the rest, and yeah, use. And now if I call this thing, yeah, I forgot to trace rev. Probably not, it's probably not gonna, yeah. Well, this is a little bit better. So that's at least something that I want to see. I would like to see the actual elements in there. You know what? It's probably polymorphic argument. That's probably what it means. It's a polymorphic argument. Can I make it print actual values if I specify that these things has to be integers? Okay, so that's probably something that we can do. So let's reuse this entire thing. Let's trace that thing one more time and then do it like perfect. You can now clearly see the whole dynamics of the language. You see, so here is the first argument, here is the second one. Right, so in here, on each iteration, we chop off the first element from the axis and we add them to the accumulator. And once we reached the end, we just return the accumulator. So look, here's the list. We take 1 and push it to the accumulator. Then we take 2, push it to accumulator. 3, push it to accumulator 4 and until this thing becomes empty, and as soon as it becomes empty we return the accumulator. So this is how we reverse it. So I really like that I can actually visualize that process, because this is how I see that in my head when I'm writing this kind of recursive things, but it's kind of difficult to explain what's going on in here. And I'm really glad that with the trace I can at least show what the hell is going on. This is actually very cool. So yeah. So yeah, that's pretty cool. And I'm gonna do a committee and then push add solution to problem 05, and I'm gonna push that right into the repo. Okay, so I'm already a little bit tired already. We managed to solve 5 problems today, but to be fair, majority of time we were primarily discussing function programming and different concepts in function programming and optimization and stuff like that. So today's stream was not about solving these problems, but more about discussion of function programming, which I find to be very productive. I think today's stream was very productive, and I hope it was very educational for people who only get into function programming. All right, so I guess that's it for today. Thanks everyone who's watching me right now. I really appreciate it. So we're gonna have more Porth streams in the future. So it's just like a, you know, random chill stream to get like a break from Porth. And then, yeah, I'm gonna go. Thanks everyone for watching. Really appreciate that. Thank you for all of the subscriptions, donations, and bits and stuff like that. Especially appreciate that. And let's maybe rate somebody, because we got rated by Mr. Provod. So maybe we want to rate somebody back. So is anyone streaming any function programming on the software development section of Twitch? Okay. So we already rated Supinic, so maybe we can find somebody else. D4 Highness, I guess. So who's D4 Highness? Is that somebody who's doing function programming? Are they doing function programming? If they're doing function programming, I'm actually down to rate them. Recursive Twitch, yeah, it just goes recursively. Almost broke my T. The fuck? It makes it really painful to rate people, like holy shit. So looks like they're alive, I hope. What are they doing? So what is this language? I don't recognize this language. It's a shell script. Oh, building blockchain on a camel. Okay, this is perfect. Let's actually read them. Okay, blockchain on a camel. Holy fucking shit. Mein God. Unbe-fucking-livable. Alright. I wish Twitch was a little bit faster. Cool. I already pressed the rate command and it's still being slow. Come on, you can do that. Twitch, come on. Okay, I believe in you. It's already showing, but it doesn't show me the button yet. That's how slow it is. Alright, get ready for the raid, boys and girls. Get ready for the raid. And I see you all next time. Love you all.